Welcome to the deep dive. Today we're jumping right into a really core manufacturing process, deep drawing, specifically for stainless steel sheet metal.
Yeah, this is absolutely fundamental stuff. I mean, if you think about high-quality seamless parts, maybe sinks, chemical tanks, even fancy boat fittings.
Things that start flat and end up 3D.
Exactly. Deep drawing is how you get there, creating these high-value components pretty cost-effectively across, well, a ton of important industries.
Well, it sounds simple, right? Just push a flat sheet into a shape. It's actually deceptively difficult.
Oh, very. The whole process is constantly fighting against potential defects. You get wrinkles, scratches.
And the really bad one, the bottom just breaking right out.
That's the catastrophic failure. And what causes these problems? It's a mix, really. It's partly the steel itself, its properties.
And partly how you actually do the drawing.
Right. The process parameters.
Yeah.
Things like how hard you clamp the sheet, the blank holder force, how fast you push the punch, and maybe most importantly, lubrication.
Okay, so that's the core tension, and we're looking at a study that really dug into this.
We are. A pretty comprehensive experimental study. They took 4 specific stainless steel grades.
The common ones.
Yeah, the workhorses.
Yeah.
Standard austenitic AISI 304 and the standard ferritic AISI 430. But then they also tested supposed upgraded versions, a 304 modified and an AISI 441. These are designed for better drawing.
Okay, so standard versus optimized.
Exactly. And they ran a lot of tests. Basic tensile tests, sure, but also 336 individual Erichsen tests. That's a standard deep drawing simulation test. Plus metallographic analysis to see what's happening inside the metal.
So the mission here is to figure out what matters more. Is it picking the better material, or is it getting the process just right?
That's it. Can clever processing make up for a less inherently formable material, or does the base material always win out?
Okay, let's unpack this, starting with the materials themselves. Austenitic versus ferritic. You described it as stiff versus stretchy.
Yeah, that's a decent analogy. If you look at the basic mechanical tests, the tensile tests, the ferritic grades, the 430 and 441, they have a higher yield strength.
Meaning they resist starting to deform? They're stiffer initially.
Right, $3 to $2 is higher. They fight back more at the very beginning.
Which sounds good, but in deep drawing, you need the material to keep deforming, right? To stretch without breaking.
Precisely. And that's where the austenitic grades, the 304s, really shine. Their basic crystal structure, the FCC lattice, it just makes them incredibly good at plastic deformation.
They can stretch a lot more.
A lot more. And they have this amazing ability to work harden. The more you stretch them, the stronger they get. That's linked to something called the strain hardening exponent, which is much higher for austenitics.
So how big is this difference in stretchiness? Can we put numbers on it?
Oh yeah, it's significant. If you look at the total elongation before fracture, what they call 8%, the ferritic steels achieve only about 40% of what the austenitic steels can manage.
Wow, so the austenitics are like 2.5 times stretchier.
Roughly, yeah. And if you measure the total energy the material can absorb before it breaks, think of it as toughness and deformation. The ferritics manage only about 1/3 of the austenitic capacity.
Okay, massive difference. And the Erichsen test, the deep drawing simulation, did that confirm this?
It absolutely did. The austenitic grades consistently got much higher Erichsen index values, the IE. So the standard 304 averaged over 13 millimeter deep draw.
Well, the ferritic 430
only averaged about 9.5 millimeter. Big gap.
What I find really interesting, though, is those modified grades. The 304 mod and the 441. They were specifically tweaked chemically for better drawing performance. Did that pay off?
You know, this was maybe the biggest surprise in the data. The modifications barely did anything, seriously.
Yeah.
They tweaked the chemistry, less chromium, more nickel in the 304 mod to keep the austenite stable. Super low carbon plus titanium and niobium in the 441 to stabilize the ferrite.
Sounds like smart metallurgy.
It does. Yeah. But the actual performance increase in the Erichsen test, it was tiny. On average, less than 0.3 millimeters difference compared to the standard versions.
Less than 0.3. After specific chemical optimization.
Yep, negligible, really.
So it seems like the fundamental crystal structure, austenitic versus ferritic, just swamps those minor chemical tweaks. That's huge for manufacturers, right? Don't just pay extra for a modified grade, assuming it's automatically better.
Absolutely. The inherent capability set by the lattice structure seems to be the dominant factor. Now, there is one property where ferritics sometimes have an edge. It's called anisotropy.
Right. That's about deforming differently in different directions.
Correct. Austenitic steels tend to be pretty isotropic. They deform kind of uniformly, like clay. Their normal anisotropy coefficient is close to 1.
But ferritics?
Ferritics, like the 430 they tested, can be quite anisotropic. Its score was way up at 2.42. This means it resists thinning more when you pull it in certain directions.
And that's good for.
It's actually really beneficial for the drawing part of deep drawing, where the flange of the metal is being pulled inwards towards the die cavity.
Ah, but the Erichsen test is mostly stretching, pushing the dome out.
Exactly. So that Erichsen test doesn't fully leverage the ferritic steel's drawing advantage. The isotropic austenitic steel, with its overall superior stretchiness, still wins the stretching contest.
Okay, so technically, austenitic seems clearly superior for pure formability, which brings up the big question. Why would anyone use ferritic then?
Now we get to it.
Money.
Money, absolutely. Ferritic stainless steels are way cheaper, like potentially half the price or even less sometimes.
Half the price? Okay, that's significant.
And their price is much more stable. Austenitics need a lot of nickel, and nickel prices, well, they bounce around a lot. Ferritics don't have that problem.
So that massive cost saving changes everything.
It does. It means a manufacturer might look at the lower formability of ferritic and say, okay, but it's so much cheaper, I can afford to spend a bit more on optimizing the process, maybe use slightly thicker sheets, maybe invest in better tooling or lubrication, and still save money overall compared to using austenitic.
Right. The cost difference buys you room to maneuver on the process side, which is the perfect lead-in to the next part. The process parameters. This is where the study got really interesting, wasn't it? Finding out which factors really move the needle.
Oh, yeah. The statistical analysis, the ANOVA, it clearly pointed to certain factors being game changers, and the absolute undisputed champion.
Let me guess. Lubrication.
Lubrication. By a mile.
And they tested different types, too, not just on or off. What worked best?
The clear winner, hands down, was using a solid lubricant film, specifically a PVC adhesive film.
Like a plastic wrap, almost.
Sort of, yeah. Applying that PVC film dramatically boosted the Erichsen index compared to running the test dry, with no lubricant.
And did it matter where they put the film?
It did. The absolute best result came from complete lubrication, putting the PVC film on both the punch surface and the blank holder surface.
Okay, cover everything. Makes sense.
But interestingly, the next best was lubricating only the punch. Lubricating only the blank holder area gave the least improvement, though still better than dry.
So helping the metal slide over the punch nose is the most critical part.
Seems to be, yes. That's where the most severe stretching happens. Facilitating flow over the punch is key to letting the material deform evenly.
Now, the surprising failure. Most people might think grease or oil, right? They tested petroleum jelly. How did that do?
It was useless. Completely ineffective. It gave basically the same result as running the test completely dry.
Wow. Why would grease do nothing?
It comes down to pressure. Deep drawing uses really high blank holder pressures to control the metal flow.
Right, clamping it down.
Exactly. And that high pressure just tends to squeeze out viscous, liquidy lubricants like petroleum jelly. It physically pushes the lubricant away from the contact zone.
Like stepping on a tube of toothpaste, it just squirts out the sides.
That's a great analogy. So you'd end up with metal-on-metal contact, dry sliding, right where you need the lubrication most. The solid PVC film doesn't get squeezed out. It stays put.
Clever. Okay, so lubrication is king. What about the other factors? Blank holder pressure and punch speed. They mattered, but less so.
They were statistically significant, yeah. But their effect was much smaller than lubrication. For blank holder pressure, maybe slightly counterintuitively, a lower pressure was actually better.
Lower pressure helped. Why?
Lower pressure, the 6.6 MPa level they tested, just makes it easier for the sheet metal to slide inwards from the flange area. It allows more material to feed into the die, reducing the stretching demand on the material already over the punch. High pressure, 59.2 MPa, restricts that flow more.
Okay, easier sliding is good. And punch speed, faster or slower?
Slower was better. Running the punch slowly, at 4.3 millimeters per minute, gave a better Erichsen index than running it fast, at 120 millimeters.
Why would slow be better?
It gives the material more time to deform. At the microscopic level, plastic deformation involves things called dislocations moving through the crystal lattice. Slower speeds make it easier for these dislocations to move and rearrange, accommodating the stress without causing a failure.
So slow and steady wins the race, but lubrication is the car you're driving.
Well put. Yeah. Speed and pressure matter a bit, but they're minor compared to the choice of material, and especially the right kind of lubrication.
And to really see why lubrication makes such a difference, we need to look at the metal itself after the test, the microscopic evidence.
Exactly. Metallography and the microhardness tests give you the proof. They looked closely at samples tested dry versus samples tested with the PVC film.
What did they see in the dry tests?
High friction. Because the metal couldn't slide easily over the punch, the deformation got concentrated. Instead of stretching evenly, the material would thin down drastically in one specific band, usually partway up the side wall of the cup. That's called localized necking.
And that's where it fails prematurely.
Right. In the very top of the cup, the apex. It barely gets deformed at all because the material flow stalled out.
But with the PVC film,
totally different story. The lubrication lets the sheet slide smoothly over the punch. The plastic deformation gets spread out much more uniformly across the whole dome. You see a consistent, even thinning all the way to the apex.
It uses the material's full potential.
Precisely. And the hardness tests confirm this visually.
How so?
Well, first, the austenitic 304 showed massive work hardening, as expected. It got much, much harder in the deformed areas than the ferritic 430 did, up to 180 Vickers points harder.
That's that strain hardening exponent we talked about.
Exactly. Now, when that 304 was tested with lubrication, the hardness increased steadily as you measured towards the apex, reaching its absolute maximum value right at the apex, zone 10.
Showing that the most deformation happened right where it should, at the deepest point of the draw.
Correct. Uniform, maximized deformation. But when the 304 was tested dry,
the hardness at the apex was lower.
Much lower, up to 100 points lower than in the lubricated test. This confirmed very little stretching actually happened there.
Yeah.
Instead, the peak hardness shifted down to around zone 7, that area halfway up the wall.
Where the localized necking happened.
Exactly. It's microscopic proof that the material flow is blocked by friction, leading to premature localized failure.
This really ties everything together. It seems the better the material's inherent ability to deform, the more critical it is to get the process right, to actually use that ability.
That's a key takeaway. The study showed ferritic steels were less sensitive to changes in parameters. Changing the lubrication only improved their maximum performance by about 10.7%.
Okay.
But the austenitic steels, with their amazing deformation capacity, they were highly sensitive. Just changing the lubrication condition could change their performance by up to 21.7%.
Wow, double the impact.
Yeah. So if you pay the premium for that highly formable austenitic steel, you have to nail the process, especially lubrication. Otherwise, you're essentially throwing away a huge chunk of the material's potential.
So it really brings us back to that selection dilemma. When you're choosing a stainless steel for deep drawing,
you're weighing things up. You've got the austenitic grade with its fantastic formability, its high work hardening, but it costs more and its price fluctuates.
Versus the ferritic option, much cheaper, stable price, but less inherently formable.
And your choice also depends on how sophisticated your process control can be. Are you willing and able to implement things like specialized solid film lubricants? Because for the austenitic grades, that kind of optimization is crucial.
It seems like getting the lubrication right, specifically using something like a PVC film, not a traditional grease, is the single biggest lever for unlocking the potential, especially of the austenitic steels.
That's what the data strongly suggests. That single choice can be the difference between a successful deep draw and a failed part.
So what's the bottom line here? The path to really efficient, high-quality deep drawing isn't just about the material or just about the process. It's a synergy.
Absolutely. It's combining the right material properties with carefully optimized process parameters.
And if there's one parameter to obsess over, it's lubrication. Getting it right, maybe avoiding those traditional viscous oils under high pressure, seems paramount.
That seems to be the clearest message for maximizing performance.
Okay, so here's a final thought for you, our listener, to chew on.
The study hinted that good process control can help close the performance gap between the expensive austenitics and the cheaper ferritics.
Right. So given that ferritic steels are maybe half the price, think about where future research might go. Could metallurgists focus specifically on boosting the properties of ferritic steels that help in drawing?
Could they, for instance, engineer ferritic grades with much higher normal anisotropy, that bar value, to help with the drawing in part, or maybe find ways to increase their strain hardening exponent to make them tougher during stretching?
If they could make ferritics behave even a bit more like austenitics in those specific ways while keeping the cost low.
The economic incentive is certainly there. Could clever metallurgy make cheap ferritic steel truly competitive for even the most complex deep drawing jobs? Something to think about.